All right, welcome back to organic chemistry. We have a new reaction we're going to talk about today. We're going to talk about the claisen reaction. The claisen reaction is similar to the aldol reaction, except now we're going to work with esters. So working with an ester, the mechanism is going to slightly change for us, right? A little bit different, but very similar. We're going to make an enolate first. Enolate is going to attack a carbonyl. Once we attack the carbonyl, then we may see something a little different that we saw with an aldol reaction, right? Let's look at that. So with our claisen reaction, we're going to use an ester. And we'll use this ester here. And we're going to use it with our base, and ET. This is going to be our first step. Second step, we're actually going to add in H3O. Okay? And we'll talk a little about why we need to add in H3O plus in there, right? Remember, we're under basic conditions, and at the end, we're actually going to have to throw in some acid in there to kind of neutralize everything, right? We'll talk about that. And so what's going to happen is this group's going to come in, it's going to react with itself, and we're going to form this type of molecule. We're going to form this type of molecule, right? We've seen this a little bit before, right? We've seen these two carbonyls attached to one carbon there, right? We're going to form this type of a carbonyl species, right? With two carbonyls attached to it, right? And so we can kind of see what's going on in terms of the mechanism, right? We're going to make our enolate here. It's going to react with itself. We're going to react with this carbonyl. But usually when we react with that carbonyl, we generally get an oxygen here with a negative charge on it, right? Which then gets protonated with the hydrogen and then could be eliminated, right? Kicked off, right? In this case here, no, we have a carbonyl at the end. So let's see the difference of that one. The big difference going to happen is with this oxygen here, right? So let's go ahead and draw the mechanism for this reaction. And what I'm going to do, instead of drawing the CH2, CH3, we'll just draw it as ET, right? That means an ethanol group, ET, okay? Again, we'll use our base. This guy we're using NaOH. And what we're going to do is, just like before, we're going to deprotonate our alpha carbon. Okay, and we get to this form here, right? Where we, again, just like we saw before, we have that negative charge on that carbon. We made an enolate, right? We made that enolate. Now this enolate is going to attack itself. Okay, so our enolate is going to come in and it's going to attack itself. Again, where is it going to attack? Which carbon? It's going to attack the carbon and the carbonyl, right? We've seen that before. We've seen that hundreds of times now, right? Written that hundreds of times is this enolate. Our nucleophile is going to attack that great electrophile there. Okay, electrons are going to go up, right? So we get to this species here. And then let's see what our intermediate looks like. All right, so we get to this step here. We got that oxygen with that negative charge on it, right? Now, previously, what would happen? This would get protonated and make an OH group here. But these electrons actually have the opportunity is they can come back down. If these electrons come back down, what has to happen? What's going to have to happen? Right? Something's going to have to leave to make room for this pi bond to reform, right? Something's got to leave. In this case here, the electrons come down. We're going to kick off what? You can't kick off like carbon. Carbons aren't gluing groups at all, right? So we're going to kick off this OET group, right? We're going to kick that group off. Okay, it's an okay leaving group. We're going to kick that off, and we'll write over here. And we get this species here, right? We've generated this compound here. Whoops, I forgot my oxygen. I lost an oxygen. Okay, and we get to this species here, right? Now, notice what happened now. As we kicked off this OET group here, we've got reformed our carbonyl, right? We got the carbonyl back with that methyl group still attached, okay? But we have these connected together now here. Now, the thing is though, we talked about this a little bit, is this hydrogen attached to these two carbons actually is going to be very, very acidic, right? It's pretty acidic. So what happens if this is in solution, it's under basic conditions, is that's going to be deprotonated by our base. And we'll draw this right here. This one can get protonated fairly easily. Remember we talked about the pK for this one? pK of this one's like around 9, right? That's fairly acidic for a CH bond, okay? So we'll deprotonate that, and we get to this form here where we have this enolate here, right? We talked about this enolate being fairly stable because it can go between the two resonance structures there. So we don't want to stop here. We don't want to end up with this negative charge on a carbon, right? So we need to do something. That's where the second step comes into play. This is where we're going to use H3O plus so that we can protonate this to give us our final compound here, which is going to be our neutral compound. So this is all for the first step. The second step then is going to be addition of H3O plus. So we'll do this right here. We're going to take that proton. That way we can get to our final compound, right? Which would be the ET. We get to our final compound shown there, right? Where we get this, we're going to be able to protonate that. So we get this final compound. We get our neutral compound here, okay? Our neutral compound. So in this reaction here with our claisen reaction, we're going to make our enolate like we saw before, right? Even though we had an OET here, we're still able to make an enolate here. You can make that enolate. We make the enolate, it's going to attack itself, that carbonyl carbon. Attacks that carbon, electrons move up to the oxygen. Now at this point here, these electrons are able to come back down and we can kick off the OET, right? Previously, when we did the aldol reaction, we didn't have a very good lead group at all. So these electrons didn't have no choice. They couldn't come back down. So we had to protonate. But in this case here, these electrons can come back down and we can kick off this OET group. Okay, this comes off. And this just comes off into the base, right? It just becomes a base, part of the reaction. Notice what base we're using, right? That's this lead group coming off here is the same thing as our base, okay? Electrons come back down, kicks that group off. We make this group here, right? We made carbonyl. Now we have 2 carbonyls. But unfortunately, this is under basic conditions. And so we're gonna have the base in here in solution, which is gonna do what? It's gonna deprotonate the hydrogen, just because this hydrogen is very acidic now because it's between 2 carbonyls. And so our second step here, this would be step number 2, is we're gonna have to protonate that. And that's why we throw in acid in there. Acid in here, this will neutralize our base and also be able to protonate our carbonyls here, okay? Protonates this to give us our final compound, okay? So we do our claisen reactions, we're gonna need 2 steps. Once the first step's with the base, second step is gonna be addition of acid in there, okay? And this will be our claisen reactions. Our claisen reaction is always gonna have an ester. Ester is gonna react with another ester or with another carbonyl, okay? It's going to be our claisen reaction, okay? Claisen reactions. Our claisen reaction, we see the big giveaway from that one is we're actually adding another carbonyl group on here, right? We're getting another carbonyl group added to our ester. Okay? It's our claisen reaction.